In this video we'll find the area of a region in polar coordinates. I'm going to look at the curve r equal to 1 plus cosine theta. Plotting that will give you a cardioid shape, a heart-shaped region in the plane. And we're going to look at that area that's enclosed by it, and I want to find the value of that area, and to do so you just need to integrate the function 1 over the region r as a double integral. Because we're working in polar coordinates, we're going to integrate with respect to r and theta, and remember, anytime you go and convert to polar coordinates you incur a factor of r, because the volume, or this area element, dA, is going to scale with the radius. What I first need to do is figure out my bounds of integration for theta. So theta will start at theta equal to 0, and we need to go all the way around, and if you do take theta from 0 to 2 pi, you will trace out this curve r equal to 1 plus cosine theta exactly once. It's very important that you realize that you're only going to trace it out exactly once by choosing those limits of integration. So that tells me that theta should be 0 to 2 pi. I'm now going to think about a generic angle theta that I've drawn here, just a typical one, and I think about a radial, the radius limits of integration, and I think about starting at the pole here and walking along that radial line until I exit the region. In this case I start at r equal to 0, and I exit, my radius is increasing, and I exit as soon as I hit the curve that's the bounding curve for the region, which in this case is 1 plus cosine of theta. So that tells me that r should go between 0 and the formula for my curve. So we have our limits of integration, and it's just a matter of calculating an iterated integral now. This will take a bit of work, so we'll spend some time doing this. I'm going to first integrate with respect to r, so I get r squared over 2, and it has to be evaluated between 0 and the upper limit of integration. And so we'll evaluate r into these expressions, and you have to be as precise as possible. I need to put all of that into r and then square. And so when I plug in 0 I won't see anything, so I just see that first term in the fundamental theorem. This needs to be expanded out, and that requires foiling. So you'll have 2 cosine theta, and then cosine squared of theta, and everything was over 2. Let's break that into individual terms now. So I'll have 1/2, that's 1 over 2, and I'll have 2 cosine over 2, so just a cosine term, and cosine squared over 2, which is 1/2 cosine squared. This term is easy to integrate, it's constant. This one's easy to integrate, but this one is a square of cosine, and in order to calculate its integral you'll want to use a power reduction formula. So I'm going to use a trigonometric identity to reduce that degree 2, and the right identity is cosine squared of theta is 1 plus cosine of 2 theta. Notice the angle gets doubled there, over 2. Let's just continue expanding all those terms out to see exactly what I have. I have 1/2, I have cosine, and then I have this 1/2 times the 1/2 there, that gives me 1/4. And I have the 1/2 here times the cosine over 2, so that gives me 1/4 cosine of 2 theta. Let's integrate each term. The constant term is 1/2 plus 1/4, that's 3/4. So integrated it becomes 3/4 times theta. The integral of cosine is sine, and then we're integrating the 1/4 cosine of 2 theta. Because of the double angle, it will become 1/8 sine of 2 theta, and then we need to evaluate that between 0 and 2 pi. Plugging in the numbers, and I'll let you check all of the calculations, but you should do that. If you plug in 2 pi and 0 and subtract, you will get 3 pi's over 2. And that is the area of the region in the plane here. In a previous calculus class, when you were just learning integrals of one variable and you were doing integrals in polar coordinates, you may have seen a formula for the area of a region between polar curves as 1/2 r squared, and integrating that with respect to theta. You can see that formula appear in our calculation earlier. Here it is right here, r squared over 2. And here is your r, it's the 1 plus cosine of theta that's being squared and divided by 2. So this is a more general situation, a more general formula, and the formula you may already have learned is really what we get after doing that first integration of the inner integral with respect to r.